Welcome to the deep dive. Today, we're tackling something big. We're looking at the future of biofuels, sure, but also this pretty radical idea for planetary scale infrastructure that could maybe solve its biggest problem.
Yeah, it's a fascinating link between space tech and, down-to-earth energy economics.
Yeah.
We're going to explore how this huge kinetic thing in orbit
Mm.
could be the key for, well, a $48 billion clean energy market.
Okay, let's unpack this then. So the biofuels market, it's growing fast, right? Like an 8.5% compound annual growth rate projected. And that's pushed by government mandates, things like the Renewable Fuel Standard in the US, the ORA2 in Europe. They want more renewable fuels mixed in.
Exactly.
But here's the catch, the big paradox. It's always bumping up against this food versus fuel dilemma.
That's the core tension, absolutely. Getting the raw materials, the feedstocks, it's expensive. Sources show things like tallow, animal fat. That can be like 80% of the total production cost.
80%, wow.
Yeah. And the industry knows the best non-food option is probably algae. But the real hurdle isn't really the biology. It's the sheer cost, specifically the energy cost.
Oh,
To grow and process algae on a scale that actually makes business sense. It just takes massive, massive amounts of capital. And, crucially, energy. It's prohibitively expensive right now.
So you can't really scale up algae biofuels without some kind of stable, cheap energy source. Which brings us to the radical solution, this orbital ring system. Is that actually feasible? Or just, theory?
Well, that's the really important distinction. This is not like the classic space elevator idea, the one that needs magic materials we haven't invented.
Right, unobtainium.
Exactly. This is different. It's a kinetic structure planned for low Earth orbit, and it spins really fast, about 10 kilometers per second.
10 kilometers a second.
Yeah. That speed generates enough centrifugal force to counteract gravity. That's the key principle.
Okay, spinning fast. But how does that make it buildable with materials we actually have today?
So the trick is, it doesn't need a single tether going all the way down. The ring itself stays high up. It uses these things called skyhooks capture points, basically. And from those, you lower much, much shorter tethers, sometimes called Jacob's ladders.
Shorter tethers. How short?
Only about 500 kilometers long.
Ah, okay. And because they're that much shorter, we can actually build them with existing strong stuff like Xylon or Kevlar.
Precisely. No need for science fiction materials. And what's really clever is the ring's flexibility. You can gently nudge it, precess it, once every 24 hours.
Meaning
The lower ends of those tethers can effectively hover over almost any point, any meridian on Earth over the course of a day. Becomes a truly global network.
Okay, I see the structure now, but let's connect the dots. How does this giant spinning ring in space fix the energy cost problem for, like, an algae farm in Arizona?
Right, so the ring itself becomes this perfect platform for space-based solar power, SBSP. Imagine huge solar collectors up there beaming clean energy down 24/7, uninterrupted by night or clouds.
Continuous power from space.
Exactly. And that stable, potentially very low-cost power source, that's the game changer for biofuels. It completely transforms the economics of algae. Those crushing energy costs for cultivation and processing, they could drop dramatically.
So algae biofuel goes from being way too expensive to potentially being cost competitive, even profitable.
Highly profitable, potentially. It solves that central paradox. You get non-food feedstock and the cheap energy needed to process it, all enabled by the same system.
And the economics of getting things up to the ring are part of this too, right? The cost to orbit.
Oh, absolutely fundamental. This is where it gets really wild. The projected cost per kilogram to ELO using this ring system is estimated at around $1.
Sorry, say that again. $1, like 2017 US dollars.
$1. Compare that to even the most optimistic projections for, say, Starship, which are aiming for maybe $10 to $140 per kilogram.
That's not just cheaper, that's a different world entirely. 10 times, 100 times less.
It's a complete paradigm shift in accessing space. And that low cost doesn't just help build the ring itself, it opens up other things. Think about new revenue streams.
Like what?
Well, you could easily supply fuel from Earth to the growing in-space economy via the ring. Or use that cheap beam solar power on Earth to produce things like methanol, another valuable fuel.
Right.
And connecting this to the bigger picture, for a company involved, this kind of project offers a huge ESG advantage. It lines up perfectly with massive strategic goals: clean energy, energy security, leadership in the space domain.
So let's summarize the takeaway here for you listening. We're looking at a potential solution that could secure biofuel feedstock without competing with food, slash the energy costs that currently hold back algae, and open up new markets in space. all tied together by one massive infrastructure project.
Yeah, it's powerful synergy. And it really leads to a final thought, a question for you to ponder. If getting mass to low Earth orbit generally costs just a few dollars per kilogram, what currently impossible industries, what resource management ideas, maybe even things like large-scale orbital manufacturing or elements of climate mitigation, what becomes commercially viable almost overnight? The potential goes way beyond just biofuels.